Thank you. So at first, I would like to thank Xue Dong for the very kind invitation. It's always great to be in Singapore. So today I'm going to talk about the reverse time migration method, but with the focus on how to solve this half-space inverse elastic scattering problems. So these are based on joint works with this is Zhiming Chen. He's my former PhD student, and Guanghui Huang. He's now in Michigan State, and also my former PhD student. And Shiji Zhou, he's now my current PhD student. Okay, so we are we are interested in solving the inverse scattering problems, and this is a classical problem. And the goal is to find the support. Let's say the support and of the obstacle from the measurement away from the scatterer. And this kind of problem has many applications. We are mainly from seismic imaging, but there are other medical imaging and also non-destructive testings. So I will start with some historical background with the Rtm method, and then go to a little bit our understanding of the method using the example acoustic inverse scattering problem, so with the full aperture, and then we go to the main focus. So this is the half space inverse elastic scattering problem, and this is I will show that what's the new difficulty, the mathematical difficulty to solve this half space problems. Okay, so the idea is that we try to find the people in geophysics told me that the variations of the background not big, 1, 2, 3. So it's very hard to use a kind of optimization method to find these details because the change is not big. So instead of that, people try to find discontinuity. Let's say derivative. If you think about derivative of a discontinuous function, then the derivative is infinite. So this is their idea. Okay. So this is exactly what this kind of method we are going to do. And so the sources. So let's say the data. The first started. So you have a shot, and then you collected the refracted waves, scattered waves on the surface, and then move to the other place, and then again another shot. So these are the data. So the background. So the governing equation here. So they started with the wave equation, but in principle, one should go to the elastic waves. Okay. So this is the data, and now so the traditional, let's say. The classical way to do this is the data fitting model. Yesterday we already heard about this kind of the difficulty of this kind of model. Like let's say because the mapping is nonlinear, then we have a non-convex optimization model to solve. And if you have this constraint, then it's a non-smooth, so it's a yield pole. So there are many difficulties. So this is the let's say the classical formulation. So by reverse time migration, people do some kind of in a different way. Okay, it's a different way. So people do like this. So they are. So we find an image. Let's say an image. The image function is defined as that. This is the forward. You have a shot. Then you have the forward solution. Okay, with some non-background. And this is the forward field. And the backward is like this. So you start from the end time. And you have the data as the boundary condition, and you solve the backward problem, and simply make the product, and make a sum of all sources and all the time. So this is the output. And this kind of method is tested. It's certainly first tested, and with different kinds of data in the engineering community. So these are the 3 groups of people. They proposed this kind of method in the same year. So, but the method has the same origin. So the origin is 1970. So started like in the geophysics community, they call the pre-stack depth migration. So at the time, people cannot solve the full wave equation. People have solved the one-way wave equation. So high frequency assumptions, a lot of let's say approximations. So this is the conventional Rtm. So you'll notice that here you have the source on the bound, the shot at the source. So the other one, so there are a lot of different versions. So if we started with you try to figure out the literature, so there are different ways to express, to describe this method. So, for example, the other one is like people call it true amplitude, common angle RTM. Okay, so the difference with the difference between this one, the conventional one is that they have this source on the boundary as a boundary data. Okay, so this has certain advantages. Okay, so if you do like this, and this is again, the imaging function is the same. So this was proposed much later, and the outcome is wonderful. Let's say this kind of picture people would dream of because you can see these highly detailed structures. Okay, so this is with the real data. Okay, so this is the Yu Zhang, and at the time he was in CGG Veritas, and he gave a summer school series of lectures in our institute, and this is from his talk. So this is the starting point of our work. So our question is that what is the image? So yesterday, so we are in the workshop which is called quantitative and qualitative. So it's this is something that we have to think about. So what is the image? How do you define the image? So why this method works? So these are two related questions that we are going to answer. So this is the starting point, and then we started with think about this the simplest. So in the geophysics literature, they always think about it in the time domain, and for us, we started with the frequency domain. Okay, so now we have a Helmholtz equation. So the method, the algorithms, they are independent. What kind of obstacle you are going to use? So it works for all kinds of obstacles. Like these are the penetrable obstacles, and these are the non-penetrable with different kind of boundary conditions. The same method, and so we use this as an example. Okay. Let me first say a few words about the direct imaging method. Yesterday, Jing already gave a talk about this different, let's say, set of methods. So let's say, for example, like for the small inclusion, and we have the like a music method, and therefore point source and the small inclusion. So we started trying to understand this music. I still don't have a theorem. So there are theorems on music in the literature, but not that satisfied. So because the conditions on the theorem, in the theorem, it's not that so, it cannot be checked a priori. So these are the difficulties. So there's still many interesting stuff about this music. And we started trying to understand this, but it turns out that we moved to RTM. So this it's still some kind of interesting stuff here. So there are several papers like Amari, so with lot of discussion with Habib. And the linear sampling, and yesterday Jing already talked about this. And the direct method is inverse, let's say, RTM. And the mathematics behind this RTM in the literature, they are mostly based on small inclusion assumption. Galia gave a talk, gave lectures in our institute, also summer school lectures. And Amari, or high frequency, mostly in geophysics, people use this set of ideas. Then you can go to the geometric optics assumptions. So these are the state of where we started. And so our try to get some new understanding without these assumptions. Okay, so this is our goal. So this is the starting point. We already you already showed this, know this identity in the Jing's talk. So this is the so-called Helmholtz-Kirchhoff identity, and this is you have a domain on the boundary. You have this is the fundamental solution of the Helmholtz equation, and here you have the complex conjugate. This is the boundary integral on the right. You have the imaginary part of the fundamental solution. Okay, so this is the identity. Okay, so now how to apply this to become a algorithm. So suppose you want to find a source in the domain. Okay, now you have the measurement of the source. You don't know the location x, but you have the measurement on the boundary of the scattered wave from the point source. Now that means you know the fundamental solution on the boundary. Okay, now you have but you don't know the normal derivative, okay? But if it's a circle, we know that we have the Sommerfeld approximation. You can replace this normal derivative by ik phi. This is the data. So then becomes this one, okay? So this is the data, okay? So this is the data, and for each point in the domain, this is the fundamental solution you know. Then you can compute this integral, okay? Then on the right, you have the imaginary part by this theorem. So if you plot this integral, then you get this kind of picture. And then immediately, you know that where's the location, the peak. The peak is the location. And this also gives us the resolution, is the half wavelength. This conforms with the traditional, let's say, the understanding of this, how to define the resolution. Okay, so these are the starting point. So this is also the idea behind all this, let's say, small inclusion.
Excuse me, even if your boundary on which you calculate is far away from your inclusion.
That's true. This is on the assumption.
It still can be far away?
Far away. It's on the assumption, far away. It's on the assumption.
Because we try it far away, the data are terrible actually. We should propagate them closer to the boundary.
So if you, this is the far field. Okay. So we are in the far field setting.
In experimental data, the farther you are, the more terrible your data.
Oh, well, so that maybe we discuss later, because this kind of method already been tested in the geophysics literature. So that's not, I think we try to understand things that are already being tested in the literature. So this is. So this is the interesting, let's say, the point is that you have this idea of point spread function. We already heard about this yesterday. So in this case, you have this is the fundamental solution, and then in the 2D case, you have the Hankel function. Then it can be expressed in this integral, and this is the interesting is that it's 0 to 2 pi. So you have the full aperture. Then if you go to the half space, you only have to 0 to pi. So these are the interesting things that we are going to use later on. So now this is for the small inclusion. So now we go to the extend targets. That means the size of the target is comparable with the wavelength. Okay. How about this? Okay. So this is the algorithm. You have this data at the source. Okay. In the full aperture case, you have the source. You solve the Helmholtz equation with the non-background. Then you get a back-propagated field, and you have the incoming wave. Okay. You simply take the integral, make the sum, and then this is the new findings in our from our analysis that one should take the imaginary part of this function. Okay, this gives us the better, let's say, resolution and also better mathematical properties. I will show you. So this is now if you use the integral representative formula, you get this is the formula. This is a very simple formula. You have the data, then you get one formula. So this is the algorithm. Now this is the far field and for scattering solution. So these are the well-known concept. And this is what we prove. What we prove. So what is the image? So this is what the image. Image is the total, let's RCS, radar cross section. This is the far field from all directions. Okay, and this is the far field of you using the imaginary part. The imaginary part of fundamental solution satisfies the Helmholtz equation. So it can be used as the incoming wave. Okay. Now you have this one as the incoming wave. You have a scattering problem. Okay. Now you can have the far field, and this is the total far field. Okay. So this is what we mean by image. So this is the definition of image. And so what we can see from this is that if the imaging point z is far away from the boundary, and this imaginary part is small. Okay, this is small. So the far field will be small. On the other hand, if z is close to the boundary, then this is big. Okay, you have already seen this picture. This is so if it's very close to the boundary, then it's big. Okay. So that means you have a large, let's say, big input, and then you have a bigger, let's say, scatter field, and you have the far field pattern, and then this imaging function will be big. Okay, so that means that this imaging function will peak on the boundary on the boundary of the scattering. Okay, so this is what this theorem tells us. And I hope so someday we can prove. There is still another thing to be proved here is the maximum principle for the Helmholtz equation. This is something that's very interesting. So when the input is small, the output is also small. So there is it's something to be proved here. So that's still not, but let's say this is what I described is heuristics, but there are still mathematical theorems to be done. A kind of maximum principle, but we all know that the maximum principle does not hold for the Helmholtz equations. Okay, so these are the. Let me show you some numerical examples. Okay, so this is the very good example, that favorite example. Now we have two objects, and the distance here is 1/2. And if you use the incoming wave, let's say the tested proper wave is the wavelength is 1. Okay, so this is the first picture, and this is the second 1/2, and this is 1/4. And you even already for 1/2, you can already distinguish these two, two obstacles. That means you need not to go to the high frequency to have the RTM works. Okay, so this is the clear, let's say, indication that the RTM will work for any frequencies. You don't need all these high frequency assumptions or small inclusion assumptions. Okay, so this is the, and the second one is that it's very robust with respect to the noise. You can go to up to 60%. We have additive Gaussian noise, okay? And up to 60%, you can still see something, okay? But if you go to the multi-frequency, that the picture, we have sharper pictures, okay? This is also a very good indication is that the image really peaks on the boundary, because otherwise it will be blurred. You have multiple frequencies. You simply add the imaging function. So this is the very robust method with respect to noise. And this can be proved because it's a linear function. There are many killings in the randomness, but we haven't done this, but I think we can do this. Okay. So this is the let's say for the kind of simple full aperture case, we have a new, let's say, mathematical theorem. And also this theorem tells us that this imaging function is always positive. It's always positive. And when I first talked to Zhang Yu, and he said, how can this be true? They don't observe it in their data. And yes, this is true only in the full aperture case. If you have half space, you don't have observed this. So these are the let's say, new findings. So if you have full aperture, you have a positive imaging function. Okay. And now we go to let's say the time domain. So we started with the time domain. So these are you have some simple, let's say, applications of the possible identity that you can obtain this kind of result. Okay, so this is I just want to have a relation. So this is in the time domain. In the time domain, RTM, okay, so this is imaging function, which is the incoming wave. We have the source, okay, and then you have the backpropagate data. We have also at the source, okay. So then you have this backpropagate. You have the data. Then this is simply now we have our frequency domain. That as expected, that this is the weighted sum, okay, weighted sum of the frequency domain RTM imaging function, okay, and the weight they are the source of f. So if you do Fourier transform, and these are in the frequency domain RTM that we already studied before. So these are the connection between the time domain RTM and the single. That means that we need to think about. Consider the frequency domain. That will give clear picture about the RTM method. Okay, so these are basically the ideas behind this RTM, and we have done several works extending this idea to the other situations like electromagnetics, and this is elasticity. This is the full space case, and the interesting thing is that in the closed waveguide you have. You have the guided modes. You can still do RTM, and it will work. Okay, so these are this work, and half space acoustics, and this is starting point for us for my talk today. And the interesting is that you can do phase list. If you don't have the phase information of the measured field, you can still do RTM. Certainly you have to change. And we have theorems say that these are two, they are the same. Okay. So these are the new findings. Once you know the mathematics, you can go to other situations behind this. Okay, extend. And acoustics and electromagnetics, and also a half space case. And this is, so if you have 3D, just an example, 3D obstacle like this is in the electromagnetic waves, then you can, using the RTM method, you can find the images. Okay, so that's not, so this it's a powerful, let's say, powerful method to direct image method to find the obstacles. And now I'll go to let's say the main part of my talk today is that we'll try to extend this kind of to deal with the half space inverse elastic scattering problem. That means we have the data collected, we have a shot, and then we collect data. But now the subsurface medium, we assume it's elastic waves. It's not acoustic waves. So these are what's the new mathematical difficulties? Okay. So some literatures. So there are not many papers on the elastic waves because it's very complicated. Mathematically, there are many new difficulties. And let me just say a few. So in the linear sampling, in the setting of linear sampling, in that group methods, there are several works. And based on in the engineer literature, so there are also several works. And they test this kind of RTM method based on the wave field decomposition. So they decompose into the S wave, P waves. There are several papers, but not much analysis, even in the high frequency case. So they just numerical computation testings. The high frequency case is only for the acoustic waves. Okay, so these are in the engineering community. And also we have papers, Amari and Kalia. They studied the time reversal. This is in the full space. And as stated, we have earlier discussions about the full space RTM for the elastic waves. Okay, so there are not much papers, let's say, works on the elastic waves. So now let me go to the half space elastic scattering problem. Okay, so we have this linear elastic operator, Laplace E. Okay, so this is the standard notation of the Lamé and constants, lambda and mu. And this omega is the frequency rho. We will later set down as a 1. And you have the free surface condition on the surface. And here, this is, we only have an example. So deletion boundary condition. It could be other situations, could be extended. I will not go to the details of this extension. So this is the forward problem. So now we have to think about how to define the boundary condition as infinite. Okay, so there are several ways, and we find that this is a convenient way, and this should be the way to define the solution. Okay, because we know from the work of Nedelec and the radiation condition for this kind of, for the half space elastic, it's very difficult. Okay, so there's not the theory in that situation is not complete for the obstacle problems. Okay, so but in the setting of limiting absorbing principle, we have already nice theorems. Okay, so now how to define a solution? Okay, scattering solution of this half space elastic problem, and the idea is that we add some positive, let's say, absorption, okay, in the frequency. And then this problem certainly has a unique solution, okay, by Lux-Milgram. Then you study the limit where epsilon go to 0 and define this as a solution of the original scattering problem. And certainly this the limit is very hard to prove to exist. So there are literatures. So these are the early backs to the 98. And if omega square is not the eigenvalue for this linear elastic operator, then we have this convergence. Okay. Now the absence of the positive eigenvalue for this operator is proved in Cine. Okay. So a slightly different setting, but it can be easily extended to this setting. So this is the way to define the scattering solution of the half space elastic scattering problem. Okay, so this is the forward problem. So now let me go to the Green's function, the Green tensor. These are the main issues that difficulties we are going to meet. Okay, so the Green tensor, by definition, is that you have a delta source. Okay, you have a delta function. Delta source, the polarization is Q. Okay, so now it's a vector wave. So this is a Neumann-Green function. That means that it satisfies Neumann boundary condition on the surface. Okay, so it's no longer a function. It's a tensor. It's a metric because it's a vector waves. Okay, so this is a tensor. You have a polarization Q. Then this is with the polarization Q here. Okay, so this is the definition, and this is already being studied, for example, in Nedelec's paper. And now we find some new, let's say, formula, simpler formula for this one, because it could be very complicated. Let me show you. So how to do this? We take the Fourier transform, and you get the spectral Neumann-Green tensor. Okay, in x1 direction. And this is the fundamental solution. Okay, you can do the similar things starting with the fundamental solutions. You can have the S component and the P component of the fundamental solution. And these are the well-studied the objects in the literature, and these are P wave and the K and the S waves. Okay, so these are and in our, because we have taken the square root of a complex number, so you always have the branch cut as the right half, let's say, real axis, and this is the imaginary part is always positive. These are the for the fundamental solution, and this is what we have. We have this, let's say, simple formula. Simple in the sense that compared to the things in the literature. So this you have everything is in one formula. So this is the Neumann function. So it's the difference of two fundamental solutions. So the traditional way should be we might think as a plus, as in the acoustic case. But if you have a minus, then the formulas they are simpler. All these expressions. Okay. So these are the things you play with, then you get this formula. Okay, so now the difficulty is that you have a denominator delta which could be 0. Okay, so these are certainly well known. They are surface waves, really surface waves, and we can prove it has only 2 zeros. Okay, so these are the formula for the Neumann-Green tensor, and now you should take the inverse Fourier transform, but this cannot be done because you have the poles of the spectral Neumann-Green tensor. Then you also again you go to the limiting absorption principle. Okay, you take the complex, let's say absorption, complex frequency, and then you take the limit, study limit, and this is the definition. Okay, so this is for the spectral Neumann-Green tensor, and this is for the Neumann-Green tensor. You should take the limiting absorption should be defined by the limiting absorption principle. Then this is the Cauchy principal value of the integral because you have the poles, and this is the formula. Okay, so this is the formula, and now we are mostly interested in the case of when the x is on the surface. Okay, the decay behavior. Now, so if on the boundary on the surface, this function is simpler. Okay, it's simpler. It can be simplified to this matrices, okay, tensors, okay. So here you have a delta prime. Now, this is the formula we are going to use because what we are trying to do is study the decay behavior of this green tensor because the data can only be collected on the finite interval, okay. So now we have to say that the things outside, they are small, or they are not important, and you have to study decay behavior. And to study this, and now we will have to go to obtain this kind of formula, and this is based on the early studies. Let's say, how do you study the Hankel functions? So in the very early days, and this is usually the transform that we are going to use. So the integral, okay, the integral here should be transformed to the integral on this path. Okay, so this is when you try to dig out the literature how to study the asymptotic behavior of the Hankel functions, and you should go to this integral. Okay, so path. So this is the way we are doing here. Okay, so this is so this integral is is L. So you use Cauchy theorem and also this transform. Okay, so this is the formula we are going to use, and this is the first, let's say, objective of our. We try to prove the decay. Okay, Neumann. The Neumann-Green tensor decays like on the surface is a 2/3 distance. Okay, this is the decay, and this is the exponential decay. This is contributed from the surface wave, and the main part is decays like this. Okay, so this is the let's say the first main difficulty of our theory, and this is something very interesting, because if you think about in acoustic case, you don't have 2/3, okay? You only have 1/2, okay? But in the elastic wave case, you really have this. This also puzzles me. So it's why this should be like this, okay? So for the Dirichlet Green tensor, this is also already clear. In the acoustic case, you already have the difference of 2 Green tensors. You have the decay of 2/3. But why this? This is something, and if you look at the spectral Green function, you will see the defined difference between the spectral Neumann Green tensor in the elastic case and also from the acoustic case. So these are the interesting things that you think of. If you think about acoustic, we don't have this. Okay, in the acoustic, we don't have this decay. Okay. So now. So let me say a few words about the mathematics. Okay, so so there are ideas. There are RTM ideas, but there are difficulties. If you go to the mathematical analysis, and I think this is something that's interesting to us. Okay, so the starting point is that how to do this kind of analysis. They all involve the estimation of the oscillatory integral. Okay, and this kind of object has already. Many years ago, maybe starting from Euler, so they already have this kind of problem in their on their desk, let's say. So one powerful tool is the method of a stationary phase. Okay, and this theorem has a lot of let's say different things, but not many mathematical theorems to write down. So this is the thing that I found it in the book of Hemander, let's say. And this is a theorem he proved. And in the simplest situation, when everything is simple, then this is what he proved. This is the main contribution. You have a station. If you have a phase, you have an integral. It's oscillatory integral. It's lambda is big. If you have a 0 of the phase, then what's the main contribution? It's like this term. Okay, people use this without thinking about what's difference. Okay, every day. So you have to go to. So this is the theorem proved in the book. So it says that dependence is like a lambda minus 1. Okay, it's already something very interesting, because for the Hankel functions, the decay is the first term. The second term is 2/3. Okay. So this is already so these are something. So this is certainly it's a sharp. But if you go to apply these things to the concrete, let's say, situation, there are difficulties. The second one is that you have assume that this second derivative is continuous. Okay, so the bound is like this, and the most important is that the C depends on this phase function in a complicated wave. Okay, so in most situations, in our situation, if you simply go to apply this, you cannot apply because it does not satisfy our, let's say, spectral Green function. Likely cannot be less simply estimated by this kind of stationary phase theorem. Okay, the most importantly, the decay is like -1/2. Okay, so this is what the method of stationary phase. So if you go to what the difficulty? Okay, if you go to apply this.
The constant only depends on the size.
In a complicated way, you don't know how it depends because you use the Taylor expansion around this stationary point. So that's you don't know the reminder. So it's a kind of, let's say, it's true, but for numerical analysts, so we are some people, let's say, in the last end of mathematics, let's say, we are interested in the final, let's say, details because we are interested in the errors. So these are the things that for us the most important things. So these are but But it's a power theorem. If you apply this, you go to the concrete example, you will not get what you have. Okay, so this is the, but so that's what we find out. So I think this is a very interesting lemma. Okay, how to estimate this oscillatory integral. Okay, so this is the lemma called von der Kopf, and dates back to about 100 years ago, and it's in the number theory. So it's from number theory. So there are interesting stuff in the mathematics. We collect things from the other fields, and no, it's correct. So they are interesting. So you give us, let's say, this is not interest. This is if you don't have the stationary point of the phase, then the decay is like this, integral by parts. You give this. Now, if you have the second derivative is bounded by 1, then the decay is 1/2. Okay. Now the interesting thing is that you have a clear dependence on the functions. Okay, on the integral. Instead of C2, here you have a clear, simpler, weaker dependence. Okay. So this is what the von der Kopf lemma tells us. Okay. And now, if you go to apply this to our problem, okay, it's still not sufficient, okay, because now for this, in our case, in the special in the application of this Green's functions, fundamental solutions, the phase function is always like cosine, okay. So now you have derivative is the derivative is sign, so the zero that don't overlap, then this can be easily proved by the von der Kopf. But in our applications, in the half space case, this integral. So this integral, if we have to think about like this component, and this is not integrable. Okay, the derivative is not integrable. Okay, so you still cannot simply use the von der Kopf. You have to go to a little bit further. Okay, because this integral, the derivative is minus 2/3, and so it's not integral. So this is, but still we have this decay. The secret is that the singularity of this function and the stationary points of the phase, they are different. They have a gap. Then you can play with, get this this decay behavior. Okay, so this is the key. Okay, and then with this you can prove the decay, the correct decay of the Neumann-Green's tensor for the half space elastic problem. Okay. Now we also need to go to the Neumann Dirichlet-Green tensor, and this is simply you have a Dirichlet boundary condition. In this situation, and the spectral, you still have a spectral function, a spectral Green tensor, but in this case you don't have poles. Okay, so this means Dirichlet-Green tensor is better. Okay, it's mathematically is simpler. Okay. This is the formula. Then we are interested in the tensors. Okay, in the tensor. This is defined like this. Okay, on the boundary. Traction tensor. Okay. Now we can also prove that it decays like this. Okay, like this. Okay, we're using our theory. Okay, so this kind of thing is proved. Let's say first in the paper in '99. Okay, but they don't, in the paper does not have this kind of dependence, okay, clear dependence. But we will use this, okay. So he's interested in the boundary integral methods, okay. But the proof certainly is different. So we go to this oscillatory integral estimates, okay. This is pointwise, okay. This is pointwise. So you have a correct decay. So for the Green. For the traction tensor of the Dirichlet-Green tensor, this is conceivable because already in the acoustic case you have this kind of. But in the Neumann case, we also can prove this. So this is something interesting. Okay, so now this is for the Neumann, for the Green tensors. Then we go to the point spread function. Okay, how to image a point. So in a half space, space. Okay. So now you have the data because you have data is the Neumann-Green tensor. Okay. Because you have point source and then you collect data is the Neumann-Green tensor. Okay. You have this data on the boundary. You can only collect the data in the finite interval minus d to d. Then you have the boundary condition. You take it as a boundary condition. You solve the half space elastic problem. Okay. Then the field is exactly the the PSF to image a point source in the half-space elastic medium. Okay, so this is from the representative formula. We can have this is what we get from this one, and this is the PSF. And so now, because of the decay of these two minus third time, you can go to limit. This is if you have the from 0 to 2 pi. Okay, so this is why important for us to study this asymptotic decay. Okay, so this is the, let's say, full aperture half space PSF. Okay, for the elastic wave. Okay, and now but again we go to the limiting absorbing principles, and using particle identity, you can find out an expression using the spectral. Because the only information we have is the spectral Green's function. So this is the formula we have. And the interesting thing is that we want to try to prove is that the main part, okay, the main part of this PSF is this function. This is in the finite interval. Okay, so finite. Okay, so the other things, they are small. Okay, so to prove this, so the first we have difference between the finite aperture and the full aperture, and because this is because of the decay. Okay, h over d. Okay, and this is the difference between these two functions, and these are all based on this oscillatory integral. Okay, oscillatory integrals, and you have this kind of decay. And this is again. Let me see. Again, an interesting point is that the phase function. The phase function for the half-space elastic waves, they have two wave speeds. Okay, p wave. So the phase function, the most difficult thing term is here. Okay, so this becomes like this kind of a phase function. Okay, this kind of phase function. Okay, so the decay is that is 1/4. Okay, so they are zeros. Okay, they are zeros, and the second derivative also has 0. Third derivative is also 0, but they have a gap. The zeros, they have gap, so you can separate in each interval and prove this estimate. Okay, so this is the difficulties, the mathematical difficulties we try to understand things. Okay, so this is, and now the main contribution is this F, this PSF. Then we can also know that, prove that this F satisfies the same, let's say, shares the same properties of the imaginary part of the fundamental solution. Okay, that means when z equal to y, you will have a peak. Okay, it decays, moves away, but you have a peak when z equal to y. Okay, and this is something that is it's not trivial. It's not just like in acoustic case you will see immediately from the first, but in the half space elastic case, it's not that trivial. So, for example, let me write down these things. This thing is positive. It's something that very interesting. So I think there are interesting stuff. It's not that so obvious. There are spatial structures of this elastic operator give us this kind of thing. So it's somehow very nice property. It's not like acoustic wave. You have a simple, but in this case, you have to go to these fine details and then to figure out what's behind. Okay. So this is you look at the picture, you will see that these are decays. Okay, but you will have a peak in these two functions, J11, J22. Okay, so these are the point spread functions. Okay, so this is why let's say my goal is that always try to prove things. Otherwise, if you do experiments, then you will get pictures. Now people, let's say professor, already asked yesterday, what's the image? As audience, you can ask the question. Then there will be no answer. You have pictures, then how to explain? How to predict? So always modeling is important. We all talk about modeling, but the predictive modeling is the goal. That means how do you predict? Okay. Confidence is not a mathematical term. Okay. So if, like a salesman is always confident. So especially in China, the medicine can cure everything. But something that's is different. Okay. So that's why if you go to mathematics, then I can explain that under this condition, this is true. Okay, so then the other things I don't know. I think this is the correct scientific way, okay, to discuss things. Okay, so but it's difficult. Okay, so especially there are so many things involved. So this is the effort. It's a lot of effort to try to prove things. So that's why I try to share this. But I don't know if it's important or not, because people say, I already know. Okay, so that's why there's something behind this kind of efforts. Okay, so for mathematical, numerical, let's say, analysts, so we always have this kind of difficulty because we connect to the people in industry, in the application, but not really solve their problem. So there's a fine difference. So that's let's say our efforts. Let's see. Okay, now. We know the point spread function, it will work. You have only take these two peaks, okay, onto these two components of the PSF, then you will get the correct solution, okay. So this is the, this is you have a matrix. You have this J is a matrix because it's a back propagate. You have, this is the matrix 2 by 2. You have 4 components, okay, and this is the, okay, so. This is the 1, 1, 2, 2. Okay, so that we proved that you will peak of order 1, when z equal to y. Okay, it decays. Okay, so it's like the PSF. It likes the PSF in the very beginning. Shares this kind of behavior. Okay, and this will be used in our theorem. Okay, and this is the property of PSF. Then. The algorithm, the Rtm algorithm, is that the idea is extremely clean and simple. I think it's a really nice idea, and the physical has very good physical interpretation. You take the data, okay, as a boundary condition, you solve the equation. This is back propagated the field, and then you product. So this is by the integral representative formula. You can write down this. Like this, okay. So you write down this is the traction tensor, and okay. So then you have the incoming wave, and the incoming wave you should also have this delta function, delta source as a boundary condition, and this is the finding. That we find out this should be the way. So this is also agrees with the early work in the engineering literature. They call the true amplitude common angle migration. So this is if you extend, you should like this. Okay, then you have the incoming wave. And then this is the integral. You have this imaging function. Okay, you have one formula. It's a clean formula, and it will work. It's a kind of magic. Let's say it will work. Okay, so it's approved to work. It's okay. So this is the formula. Okay, so now I will go to the theorem. Okay, so now we have already proved that the properties of the PSF. Okay, so the theorem shares the same view. Okay, the same framework. You have this PSF as the incoming wave. Okay, and this is not that obvious. I will show you later on what this F is. Why it satisfies the elastic wave equation? Okay, so this you have as an incoming wave, and then you have the scattered field. So then this is the expression from our theorem. In the full aperture case, it's simpler. It becomes this far field, but in the half space you don't have this, and that means we have to go to further explain what this is. Okay, what this image is, and this is this will tell us that. If z and x they are far away, then this will be small, okay? But not more. So to go a little bit further, and we go to the limit, the high frequency limit, to say more about this imaging function, okay? So now let's see what this f is, okay? The f can be written like this, okay? So this is planar waves. This is planar p waves, and this is planar s waves. They are different, okay? So you see, they are different. Plane P waves and S waves, they have different formula. Okay, so the formula is like this. Okay, the P waves looks like you have a direction, instant direction tau, and here have a tau in the front. If you have for the S wave, you have the orthogonal wave field. Okay, so this is in this, and this is incident direction. So these are the planetary, the planar P and S waves, okay? Different in structure, okay, different structure. And exactly in this case, they have the same structure, okay? So this PSF, okay? So that means this function is the weighted sum, weighted the superposition of the planar P and S wave, and so they satisfy the elastic wave equation. So it can be used as an incoming wave. And we already showed that it decays when the distance is large, and from this we know that this imaging function is small. When it moves away from the boundary, this is the definition of let's say we will use this is so-called the scattering coefficients. So you have a plane wave incidence, and this is the total field, the normal derivative, okay, on scatterer, and there is a relation, there is a scattering coefficients, and this is extension of or things for the acoustic wave. For the elastic waves, they're not these kind of things. They're not discussed in the literature. That's why we try to extend these ideas to elastic. This is the scattering coefficients, and then this is an interesting thing. It's still not proved, and I don't know. Maybe you know better know these kind of things behind this. So okay, so I still have 10 minutes. I think no time. Oh, I'm sorry. So it's already finished. Okay, let me be quick. Okay, 2 minutes. Okay, break down. And this is the Kirchhoff approximation. That means that the incident direction on the back part is 0. And this is a very good approximation. And we do the numerical computations, but it's the proof. The proof is missing for the elastic wave. Okay, for the acoustic wave, you have the theorem of Melrose-Taylor micro-local analysis, but for the elastic wave, we couldn't find it in the literature. So there are things, but it's a very good approximation. If you do like this, then we can have let's say high frequency. Let me go. This is if you go to the high frequency and the Kirchhoff approximation, then we can get this expression. It tells us that what is the image? The image is inversely proportional to curvature on that point. Okay, so this is the final result. And it also tells us that if on the back part, and this is small, okay, this refraction scattering coefficients by Kirchhoff is 0. So the back part cannot be imaged using this RTM. Okay, so this is the explanation. Okay, so this is, let me go to the picture. Is you can expect you will work. Okay, so because otherwise it contradicts to our theory. Okay, so there you have two objects, and you have if noisy data, then you get all this sharper data. Okay, so these are not a problem. Okay, okay, let me skip. So thank you very much for your attention.
Maybe a very quick question. Yeah, please.
When you talk about time-dependent data, actually solution of forward problem is in question if your coefficient is not sufficiently small. For data function, it's not trivial to prove existence of the solution of the forward problem.
Yes, that's why these papers, let's say, the papers of I quoted, they have it's 40 pages. It's a huge number of formulas. It's not that simple. The proof of limiting absorbing principle is not simple.
No, just existence.
This is
solution of the Cauchy proof for the time-dependent wave equation with non-constant coefficient.
okay. So
It's not trivial.
sure.
Unless this coefficient is sufficiently smooth and the geodesic lines are regular.
This is on the high frequency assumption. So this plays back to the question how to prove the wave equation. What's the boundary condition for the wave equation at the infinite? You can say it's a 0, but can you prove with 0 boundary condition you can have the uniqueness and the existence of the wave equation? It's not that simple. So you think about this. Everybody thinks about the wave equation. You go to the textbooks, they are all 0 boundary condition in the final. So this is simple, but unbounded domain, how to do this? And this is why we early days we do Laplace transform to prove this kind of things. So these are the far away. So, but let's say, as I said, there are things that, okay.
Okay, so because of discuss after this. Okay.
Thank you.
So thank you again.